Hello everyone, I'm Jong Yang. Today I will present the paper Deep Recurrent Survival Analysis. This paper introduces a deep learning approach for survival analysis. More specifically, it models sensor time to event data using a recurrent neural network. In this presentation, I will first introduce the basic concept of survival analysis. Then I will analyze the DRSA paper section by section. Okay, what is survival analysis? Survival analysis is a branch of a statistic that analyzes the estimate time it takes for an event to occur, such as the death of a biological organism or the failure of a mechanical system. The word survival often makes us think of medical study, but the idea is much broader. In medicine, the event can be death or relapse. In service platform, the event can be cancellation or jump. In engineering, it can be equipment failure. In recommendation, it can be busy or clear or auction win. The important point is that survival analysis focus on time. The key question is not only whether the event happened, but when it happened. So compared to the ordinary classification, survival analysis is more time aware. Why is it different from regression? It's sensory. In ordinary regression, we usually have an input X and a clear target value Y. But in survival data, each sample is usually represented by an input X on observed time and a status indicator. If status equal 1, it means the event was observed. If status equal 0, it means the event was not observed before the observed ended. This case is called sensory. It is different from the regression. For example, suppose we observe a patient for 5 years. If the patient died during the study, we know the exact event time. But if the patient is still alive when the study ends, we know only the survival time is longer than 5 years. That's called is right sensory. Next, survival analysis is usually described using three core functions. The first is survival function, which means the probability that the event has not occurred at the time t. The second is hazard function, which represents the instantaneous risk of the event at time t, given that the subject has survived until the time. The third is cumulative hazard function, which represents the accumulated risk up to the time t. These functions are central to survival analysis and are also important for understanding the RSA. And we'll have a brief look at the method. Major category of survival analysis method. Survival analysis method can be divided into several categories. The first category is in non-parametric methods such as Kepler-Meyer. This method make few distribution assumptions, but they have limited ability to use complex individual features. The second category is semi-parametric methods such as Cox proportional hazard model. This method can use coverage with relatively weak distribution assumption, but they still rely on assumptions such as proportional hazard. The third category is parametric method, such as waveform or exponential survival model. The fourth category is deep survival model, such as DeepSurv and DeepFit. This model use neural network for long non-linear feature representation. They are say belong to this deep survival modeling direction, but it introduces a recurrent structure to model the temporal dependence across time interval. So first, Kepler-Meyer estimator. Kepler-Meyer estimator is one of the most basic methods for estimating survival cost. Its key idea is simple. At each event time, we look at the risk set, which means the subjects who are still under the observation and have not yet experienced the event. Then we'll calculate the proportion of subjects who survived past that event time. By multiplying the survival proportion over time, we obtain the Kaplan-Meier survival curve. This curve decreases step by step over time. It drops only when an actual event occurs. Sensor samples do not directly cause the curve to drop, but they still contribute to the risk set until their observed time. The strength of Kepler is that it can handle sensor data without discarding it. However, its limitation is that it is difficult to incorporate complex individual features. For example, we want to use age, gender, health status, and treatment type together to predict an individual patient's survival probability. Kepler-Meyer alone is not enough. So, cost proportional hazard model, a representative survival regression model, is cost proportional hazard model. The model is written as this. And here, H is baseline hazard. Based on individual features, this model allows us to interpret the effect of each curve variable. If beta bigger than 0, the hazard increase. If beta lower than 0, the hazard decrease. Also, exponential of X transpose beta is interpreted as the hazard ratio. the cost model is powerful because it can use individual covariates without directly assuming a specific survival time distribution. However, it relies on the proportional hazard assumption. This means that the hazard ratio between two subjects is assumed to be constant over time. In real-world data, this assumption may not always hold. This motivates more flexible survival model. The next survival model is Webb's survival model. The Unlike the Kaplan-Meier estimator, which directly estimates the survival curve from the observed data, the Webb model assumes that the survival time follows a specific mathematical distribution. The survival function is written as this. Here, S represents the probability that an individual survives longer than time t. The Webb model has two important parameters. The first one is the scale parameter, alpha. The second one is shape parameter, gamma. If gamma is bigger than 1, the hazard increases over time. If gamma is smaller than 1, the hazard decreases over time. If gamma is same 1, the hazard is constant over time. So the main advantage of web model is flexibility. Compared with exponential model with some constant hazard, the web model can represent increasing, decreasing, or constant hazard patterns. However, it still has a limitation because it assumes specific parametric form. So why do we need a recurrent survival model? Now we can remove toward DRSA. The previous method provided useful tool, but DRSA argued that the survival analysis need a more sequential view. In survival analysis, time intervals are not independent. If an event did not occur in the first interval, that information affects the probability of the events in the second interval. If the event still did not occur in second interval, that affects the third interval, and so on. Therefore, survival prediction naturally has a sequential structure. The key question of DRSA is, can we model survival better by sequentially predicting the conditional event probability for each time interval? This is why DRSA uses a recurrent neural network. It models the conditional hazard over time interval and connects them sequentially. Deep recurrent survival analysis. First, we look the abstract to understand the problem and the claim contribution. Second, we look at the introduction to understand why survival analysis need a new modeling perspective. Third, we examine the relative work to see what previous methods missed. First, we analyze the method where the RSA model hazard over time using recurrent computations. Fifth, we review the experiment, including dataset, metric, result, and evaluation studies. Finally, we conclude with the key message and limitations. The core story is this. The RSA turns survival analysis into sequential conditional probability modeling over time intervals. So first is abstract analysis. In the abstract, the paper describes survival analysis as a problem of handling time to event information with data censorship. This means the model must predict event time while dealing with samples who through event time are only partially observed or completely unknown. The paper argues that existing methods often rely on cross-counting statics, distributional assumption, or weak temporal dependence modeling. To address this, DRSA combine conditional probability prediction with survival analysis. The important point is that the paper is not simply saying, let's use RNN. Instead, it proposes a fine-grained conditional probability view of survival analysis. In other words, DRSA predict the conditional event probability at each time interval while keeping sensor sample inside the learning objective. This is the main contribution claim in the abstract. The introduction explains why DRSA is needed. The paper starts from the observation that survival analysis appear in many real-world domains, including clinic survival prediction, custom lifetime estimation, and market modeling. In all of these applications, event tracking may stop before the event is observed. This creates sensor loop. The paper also criticizes direct event probability prediction. If we directly predict the probability of an event at each time point, we may ignore the dependence between neighborhood time slices. Also, because the event is only observed at one time point, the learning signal can become sparse. DSA address this by modeling the probability of an event in each time interval, conditioned on the event not occurring before that interval. So the introduction reframes survival prediction as a sequential probability modeling problem over entire timeline. The relate world section can be divided into two streams. The first stream is traditional statistically survival analysis. Kaplan-Meier and Nelson are a non-parametric counting-based method. Cost and lasso cost and semi-parametric method Exponential and variable model are primitive methods that assume a survival time distribution. These methods are useful and interpretable, but they can be limited when modeling complex nonlinear feature interactions. The second stream is machine learning and deep learning method. Examples include survival random forest, SVRC, MTLSA, DeepSorb, and DeepFit. These methods try to improve nonlinear feature modeling and prediction performance. However, DRSA argue that previous methods still have a bottleneck. Some methods rely on distribution assumption, while others treat time being as isolated output. DRSA change this by recurrent predicting the conditional hazard for each individual over time. Here is method. Now let's look at the method. DRSA represents the survival log as this. Here xi is the observed feature vector, theta is true event time, is the observed time. For a sensor sample, now let's look at the method. DRSA represents the survival log as this D. Here Si is the observed feature vector, Zi is the true event time, Ti is the observation time. For unsensor samples, the true event time Zi is observed. For sensor sample, Zi is unknown, but we know that the event time is later than the observed time. The goal is estimate P for each sample. This means the model aims to learn personalized event time distribution for each sample. The paper also defines the survival function like this. This is the probability that the event has not occurred by time t. The event occur function is w. This is probability that the event has occurred by time t. So the RSA is not just estimating a population level survival curve. It is learn or individualized event time distribution. DLSA uses a discrete time model. The timeline is divided into interval V. For each interval, DLSA defines the conditional hazard. This means the probability that the event occurs in the current interval, given that it did not occur before this interval. For example, if a user has not charmed until day 1, the model predicts the probability of charm during day 2. If the user has not charmed until day 2, the model predicts the probability of charm during day 3. This conditional structure is very important because survival analysis is inherently sequential. The event probability at the current time depends on the fact that the event has not happened before. This slide shows figure 1 from the paper, which illustrates the DLSL recurrent computation graph. At each time slice, the model receives the feature vector and the interval information as input. The recurrent cells, such as an island or STM cell, pass hidden information from the previous interval to the current interval. This hidden state carries previous survival information along timeline. The output of each cell is the conditional hazard HI for the current interval. The key point is that the RSA does not predict each time being independently. Instead, it connects time intervals through recurrent computation. This allows the model to capture temporal dependence and give more structural supervision through the chain rule construction. After obtaining the hazard value from the recurrent network, JLSA constructs the survival curves. The survival rate is computed as the product of non-event probability. This means that to survive until time t, the event must not occur in every previous interval. The event time probability for interval I is computed as pi. This means the subject survived before interval I, and then the event occurred in interval I. This is where the probability chain rule becomes important. DRSA does not directly output the full event time distribution. Instead, it fills the distribution from recurrent hazard output. This connects all time intervals into a single sequential probability model. The loss function is another important part of DRSA. DRSA uses both unsensor and sensor sample during training. First, LZ is the event time likelihood loss. It is used for uncensored sample because their two event interval are known. The model is trained to assign high probability to the observed event time. Second, non-sensor used uncensored sample to supervise survival status. After the event occurs, the survival probability should decrease. Third, L-sensor use sensor samples for sensor data. The true event time is unknown. However, we know that the event did not occur before the censoring time, so the model should assign high survival probability up to that observed time. The final objective is this, where LC is non-censored plus L-censored. The novelty here is not merely using L-stamp. The loss design allows sensor sample to provide useful supervision. Sensor sample tell the model no event occurred before this observed time. Experiment dataset and task. The paper evaluate DRSA on 3 real-world datasets. The first dataset is clean. This is medical survival task. The goal is to estimate time until death and event probability use physicalized variable. The second dataset is music. This is a user lifetime predict task. It predicts the elapsed time from the last visit to the next visit or last FM. The third data is fitting. This is an advertised task. The goal is to estimate winning probability or market price on the sensor losing auction logs. This dataset covers three different domains: medicine, user behavior, and advertised market. This experiment design supports the paper claim that DRSA can model survival data flexibly across different types of applications. The paper used two main evaluation metrics. The first metric is C-index. C-index measures whether the model correctly orders pair or sample by predicting event risk or event time. A higher C-index is better. The second metric is ANP, or average relative log probability. ANP measures how much probability the model assigned to the observed event time. Lower ANP is better. The paper compared data set with several baselines. The statistical and semi-informatical baseline include KM and less. The distributed-based tree-based multitask learning baseline include Gamma, STM, and MTLSA. The deep survivor baseline include DeepSurv and DeepFit. This means DLSA is compared not only with classical survivor model but also with strong deep learning baseline. This slide shows type 2 from the paper. In terms of C-index, DLSA achieved the best performance on the all three dataset. On clinic, DLSA achieved 0.774. On music, it achieved 0.892. On bidding, it achieved 0.91. This means DLSA is effective at linking event time correctly. In terms of NLP, DLSA also achieved the lowest value on all three datasets. On clinic, the ANLP is 3.337 on music, this is 5.132 on bidding, it is 4.274. This means DLSA also fit the event time probability distribution well. Overall, the main result type support the claim that sequential conditional hazard modeling improves both ranking, performance, and probability modeling. In the evaluation study, the paper compared the full DLSA objective with variant that removes some loss component. The full DLSA model achieved the best index across clinic, music, and bidding. This shows that using all loss components is helpful for ranking event time. The evaluation also showed that sensor loss matter, in particular DLSA, improve performance strong on bidding, which suggests that sensor auction low provide useful survival supervision. However, not all metrics align perfectly. For example, DLSN achieved the best clinic NLP while full DLSA is the most consistent overall. So the main takeaway is that censored and uncensored supervision both matter, but different metrics may emphasize different aspects of the model. The slide show figure 2 and figure 3 from the paper. Figure 2 show the learning curve. These curves support that there is a composite during training. Figure 3 show forecast survivor and event probability curve. This is important because DRSA does not only produce one predict event time, instead it produces a survivor curve and an event probability distribution over time. The figures support the intuition that DRSA can assign high event probability near the two event time while also generating a personalized survivor curve. This visualization helps us understand the practical output of DRSA. It can also support how likely it is subject to survival until this time, and when is the event most likely to occur. Conclusion. To conclude, the key contribution of DRSA is that it reframes survival analysis as recurrent conditional hazard modeling. Instead of directly predicting the event time, DRSA predicts the conditional hazard at each time interval. Then it reconstructs the survival curve and event time probability using the probability chain rule. The strengths of DRSA are clear. First, it directly handles sensor data. Second, it avoids strict survival distribution assumption. Third, it learns personalized time-dependent predictions. However, there are also limitations. Because time is discrete, the interval design can affect the result. Also, compared with cost model, DRSA is less interpretable. Finally, because it is based on RNA, it may be less scalable than modern attention-based model for very long time horizon. The best one sentence summary is there is a predict the conditional hazard at each time interval with an RNN, then use those hazards to fill the survival curve while learning from both censored and uncensored samples. So in this presentation, the most important point is not just the equation. The most important point is why the hazard is conditional and why sensor data still provide useful solution. This concludes my presentation. Thank you for listening.